All right, welcome to chapter 6, the second video of chapter 6 of elementary statistics. Now, if you haven't watched the first video yet, make sure you've watched the first video before watching this one. In the first video, we explained there is an example of a family population of 4 people, and 2 of them are voters, and 2 of them are non-voters. So here, let's just recap the notation. We have the population size equals 4, and the voters in this population, the big X is equal to 2. And by the way, please make sure that you pay attention to this notation because this is pretty standard notation for our course. We'll be using these notations from now on. And also we know that the non-voters in this population is equal to 2, that's obtained by big N 4 minus the big X 2. And we know the population proportion of voters, the small p, the true proportion of voters is 1/2, is the obtained by dividing 2 by 4. And we also know that we can choose samples of different size. Of course, this small n doesn't have to be 3, but it can be 3. It can be anywhere between 1 and 4 inclusive. So let's say we choose samples of size n, a sample of size 3, n equals 3, and we also know that the number of voters in this sample is 1. So this is assuming that we chose a sample of size 3, one of them is a voter, the other 2 are not. And then the numbers of non-voters in this example is equal to 2. And then we have the sample estimate of the population proportion voters, p bar, is equal to 1/3. In this case, p bar is not the same as p as expected because they are usually not equal. They could be equal, but they are usually not. And the p bar is only an estimate of p. All right, the unbiased probability says that if you have a population size big N and the true proportion of something with the probability A, let's say a voter, is small p, and then if p bar is the proportion of A's in the sample, and then the mean value of p bar or the expected value of p bar over all the possible samples of size n is p. So what it's saying is that you tell me a fixed sample size. Let's say the fixed sample size small n is 3, as in our example, and you consider all the possible different samples of size 3, and then for each such a sample, you calculate p-bar value. Of course, this p-bar value may be different from sample to sample, but once you calculated all those p-bar values and you take the average of all the p-bar values, you should get exactly p. You should get exactly p. And the bias is not a property of an estimate from one sample. You cannot say a sample is biased. It is the property of an estimate averaged over all the samples. So here, let's take a look at this example. Suppose that there is a manufactured lots of 1,000 tubes, and you choose a sample of 50, and you like to inspect these 50 tubes, and how many of them are defective. So in this process, suppose we hire an inspector to do it. However, his counter has the one stuck in it. So whatever number that he tried to inspect is always shows as 1 too large. So for example, if the real number is 3 and his counter will show 4, if the real number is 20, his counter will show 21, etc. So now we can ask this question: what is the bias of his estimate of the proportion of the defective? What is the estimate? Well, the answer is he estimates this p by the p bar star, which is the p bar value plus 1 over n. And here is plus 1 over n because his count is always 1 larger than the actual value. And now when we can calculate the proportion, we divide this by the sample size n. Or in other words, in this particular case, the small n is equal to 50. So in other words, the p bar value, p bar star, is always 0.02 larger than the corrected p-bar value. So we have a bias which shouldn't exist in the first place because of because of the unbiased property. However, the bias does exist because something is wrong. And now the next example is, let's say we fix the counter problem. There's nothing wrong with the counter. We can count accurately finally. And let's say we look at all the 50 tubes and we found that 2 of them were defective. So the estimated p-bar value is 4%. So we're going to do 0.04. And now later, when we, for some reason, we checked all the 1,000 of them and we find the actual p-value, the defective rate is 3%. It's 3%. Now, my question to you is this sample biased because our p-bar value is greater than the actual p-value? The answer is no. You can't say that. Bias is not a property of a single sample. It is the property of a method of estimation or a method of sampling. It is a long-run idea, not a one-sample concept. So we can't say any sample is biased, although the p-bar value shown from the sample may be different from p-value. Actually, in many cases, they are different. They may even be very different. However, you should never say that a sample is biased. And now let's introduce what is a statistic and what is the difference between a statistic and parameters. A statistic is a formula for computing the observed proportion. So something from the observed proportion is called a statistic. And on the other hand, something that is talking about the population is called population parameters or parameters. So here, the difference between a statistic and the parameter or population parameter is whenever we use this word statistic, we're talking about samples. Whenever we use the parameter, we're talking about the population parameters. And typically we use statistic, the plural form of statistic, we use statistics to estimate parameters. For example, you can observe the sample mean from a sample that is a statistic. You use that number to estimate the population mean, which would be a parameter. Now let's talk about the variance. And we in the first video for this chapter, we looked at how to calculate the variance and by just counting. And of course, that method is not very efficient, and when the sample size is big, or when the population size is big, and this method becomes very complicated. So here we like to have a factor, we have like a formula for computing the variance. We have actually 2 variance formulas. One is applicable for the variance without replacement. One is for with replacement. The without replacement formula is slightly more complicated. It's written like this. So it is a product of 2 terms. One is the p times 1 minus p over n times another factor, big N minus small n over the big N minus 1. Of course, we need to explain what each of those things means. The small p is the population, is the true proportion and of whatever properties we're discussing. So for example, if we are talking about voters, the p-value would be the true proportion of voters, and the small n is the sample size. The big N is the population size. So once you know the true proportion, the sample size, and also the population size, you can calculate the variance. And notice that we can rewrite the formula in this way. And here in the numerator, there's a p times 1 minus p. That is what we call the population variance. We'll talk more about that in another slide. And also this factor is called the improvement factor for sampling without replacement. So even though I have it on the slide, I'll write it down in red just to emphasize that this is variance of p bar. And here is, of course, we'll talk about without replacement. The variance of p bar without replacement is calculated by p times 1 minus p divided by the small n times the big N minus the small n divided by the big N minus 1, the big N minus 1. So this is the formula. And now let's look at this example. Suppose we look at the same population, the Williams family, where the population is of size 4, and then we're going to do the big N equals 4, and small n equals 2. Let's do sum of size 2, and then we know the true proportion vote is 1/2. So in this case, the variance of p bar can be calculated directly from this formula. So it's p times 1 minus p. So it's 1/2 times 1 minus 1/2. 1/2 divided by the small n, which is 2, and then times the big N minus small n. So it's times, and the big N minus small n will be 4 minus 2, and divides by 4 minus 1. So the answer is going to be equal to 1/12. And if you simplify everything, you should get 1/12. And you see this is a much faster calculation than what we did before. And I do want to point out that you might just in case you're curious, is there any simple formula for the mean absolute deviation? The answer is not as I'm aware of. And of course, some software can do it for you, but I don't think there is a simple formula like this. And let's talk about this formula a little bit. And first of all, what if the small n is equal to 1? If you think about that, look at this formula. If the small n is equal to 1, this denominator is gone, is 1. And also, this factor becomes the big N minus 1 divided by the big N minus 1. So that thing becomes 1 also. So the whole thing becomes p times 1 minus p. That is what we call the population variance. So the variance means the variance of the observations of samples of size 1. And we can also call it a binomial observation. And let's look at the next example. Suppose we have a population of 3 A's and 2 non-A's. So we have an A1, A2, and A3. You can think about this voter, a non-voter, or whatever you can think about. And then the 2 non-A's, let's call it N1 and N2. So here, what we want to do is calculate the number, the variance of number of A's of samples of size 1 and the population variance. So here, we're doing basically 2 things. The first thing is we're doing the numbers, the variance of number of A's for samples of size 1. And then the second thing is we're also doing the population variance. So let's discuss this in detail. So the first calculation is, what is the variance of numbers of A's of sample size 1? Of course, for sample of size 1, you have 5 different samples, and they will give you different p-bar values. If you choose an A, then the value of p bar is 1. If you choose an A2, the value of p bar is 1, and choose A3 is 1, and etc. So you have 3 1s. But on the other hand, if you choose sample of size 1 being N1, this becomes 0, and then N2 will also give you 0, and so on. So, and also we know the p-value, the true proportion of A's is equal to 3/5. It's equal to 3/5. So this is the true proportion. And now let's calculate the variance of p bar. So the variance of p bar is equal to, for each of the values, we're going to subtract it by the p 1 minus 3/5 squared, and then plus, here is squared, and plus, well, actually we have 3 such terms. You can just multiply by 3, and plus 0, it's 3/5 by the way, 0 minus 3/5, and then we square it, and then we're going to divide it by 5. So the total number, if you put everything into the calculator, you should get 6/25. So this is the direct calculation shows it's not too complicated, it's doable. But on the other hand, we can do a different calculation. It should also be equal to p times 1 minus p. This is population variance. So when p is equal to 3/5, and then 1 minus p, of course, is 1 minus 3/5, the total answer would also be 6/25. As you can see, the second calculation is easier, simpler than the first one, so it's recommended. But if you want to use the first one, you should get the same result. And also, let's look at let's look at this denominator of this factor, the small n. Think about that. If you have a larger sample size, or in other words, if you make this small n bigger, if this small n bigger, and then this whole fraction will become smaller. And also for the second factor, because the small n is bigger and the numerator is also smaller. So all those things are working together will result in a smaller variance. Or in other words, as the sample size increases, the variance of p bar will decrease. So here, in the extreme case, if the sample size is the big N, if the small n is equal to big N, and then the second factor becomes 0, and therefore the whole variance becomes 0. Or in other words, in that case, you don't have any variance at all. The variance is 0. And if the sample size 1, as we discussed before, and this variance of p bar is p times 1 minus p. As the sample size and small n grows, the smallest possible sample being size 1, the largest possible sample size being n, and then the improvement factor goes down from 1 to 0. And therefore, so these two would pressure descend the variance p to 0. So the variance of p would decrease from p times 1 minus p all the way to 0. And in most of the practical problems, this big N is huge. This big N is not like your 10 or 4. This big N is very large, like hundreds of thousands or even millions. If we just neglect this big N minus 1, I mean, this 1 in the big N minus 1 just replaces by big N, this would not cause much difference to the results. So here, the second factor, the big N minus small n over big N minus 1, is approximately big N minus small n over big N, which can be rewritten as 1 minus small n over the big N. Or in other words, we can call it 1 minus f, where f is the same as big N, small n over big N, the sampling fraction. Or in other words, what proportion of the population is used in the sample. So there are some small gains from the finiteness of the population. Let's look at what I mean by that. So here, let's n infinity be the sample size be drawn from the infinite population. So what that means is, let's say there is a hypothetical infinite population. The population is infinite. And then we can draw some finite sample size. You have infinite population, just draw 30 of them, for example. And also we can draw the same sample size, let's say 30, from a finite population with the same p. Then, in order to have the same variance, and we have the n f, the n, the big F, the small n, big F, small f, is approximately n infinity times 1 minus this n infinity over the big N. So this is actually coming from the previous slide, and from this formula, when we let this big N grows really, really big without a bound. So this is we have a hypothetical infinite population, and then so here's what happens. So let's say this is we have a set of infinite, so this is infinite population, and then we have a sample of size nf. So this will give you approximately same precision or the variance as you have a population size n. Now you choose this is actually infinity. This is n. I'm sorry, let me just erase this. This is n infinity, so you choose a sample of size n infinity, and this is approximately give you the same precision as you choose nf of them from a finite population. So let me illustrate using the next example. So in our next example, suppose that you have several populations. One is the hypothetical infinite population, and then we have a voting population of the US. At the time of writing the book, it was 120 million. And then you have the voting population of Illinois, which is 6.5 million. And then Oklahoma is 1.5 million. In Albany, Georgia is 32,000, etc. So if we take the sample size 3,000 from the hypothetical infinite population, what sample size will we need from those finite populations in order to get about the same precision or the variance? So here, what we have is this n infinity is equal to 3,000. So now we want to find what would be a reasonable sample size in order to get the same precision. So we use 3,000 times 1 minus 3,000 divided by the population n. So, and then we can find this value for different values of n. So, for example, here, in the first example, so let's do 3,000, let's do R times 1 minus 1 minus 3,000 divided by the big N. In this case, big N is 120,000. So this result is equal to 2999.9 something. So this answer is almost the same as 3,000. So, or in other words, for this voting population of the US, you can pretty much choose the same 3,000 as the sample size. How about a bigger state like Illinois, 6.5 million. So 6500000, and this will give you about 2999. Also, it's getting a little bit smaller, and then 3,000, but it's about the same. And then the next one, you're gonna do a even smaller state like Oklahoma, 1500000, and this will give you 2994. You get a whole number 2994. So you see the sample size does go down a little bit as the population goes down, but it's not going down that much. And then how about a smaller town, only 3,200 people? So that would be 32,000. And then the population size will goes down to about 2,718 or 19. So this is the population. What we're saying in this example is, if you can choose 3,000 people from the hypothetical infinite population, or 3,000 from the whole voting population of the US, or 2,999 from the voting population of Illinois, or 2,994 from the voting population of Oklahoma, or about 2,700 from the voting population of a small town in Georgia, they would all give you about the same precision. So that gives you a kind of idea what would be a reasonable sample size as the population size varies. And of course, you may find, hey, this is confusing. What is the infinite population? You can't really do it. Well, here's the thing. We can actually think about this as the sampling with replacement. Think about that. You have a population that's even in the Williams family as small as 4 people. But if you're allowed to put people back. So for example, when you do the sampling, you can actually choose the father as the first element. But if you're allowed to put him back before choosing the second element, and then you can keep choosing this forever. So the population essentially becomes infinite. The population essentially becomes infinite. Also, let's go up, look at this formula. When this big N tends to infinity, the whole factor tends to 1. If you want to convince yourself why this is true rigorously, you will need a little bit of calculus, but you can probably intuitively understand that when the big N is really, really big, then compared to this big N, the small N, and 1 is like nothing. So the whole thing is be more and more like 1. And so in the theoretical infinite population or sampling without replacement, you're going to get a variance. We have a very nice formula, the P minus, times 1 minus P divided by N. So this is the nice formula for the sampling with replacement. I'm going to write it here. So in this case, so here the variance of P bar, here, of course, and you specify this is with replacement, is equal to P times 1 minus P divided by the small n. So this is the sampling with replacement or from the infinite population, either way. So this is the example. So let's look at this example. So for example, let's say we do the Williams family, and if you choose the sample size 2, but now we do the with replacement. So now you're going to get 1/2, 1 minus 1/2. This is minus, and then divide by the sample size. Let's say we do sample size 2. So eventually you're going to get 1/8. So for example, Williams family, if we do it's sampling with replacement, and then the variance will become more like 1/8 instead of 1/12. I'll give you an optional exercise to do this calculation by hand, namely using the previous method, old method, the lengthy calculation without using the formula. You should get exactly the same result. All right, so now let's say a few words about quality control. In many of the quality control of manufactured products, and we may draw some random samples from either a production line. Production line means you have a production line to keep producing the products. In that case, you can more or less view this population as infinite, or you can also draw it from a complete lot of the material. Let's say we manufactured 10,000 objects, and that's it. No more is being manufactured. So you can think about this as a population of 10,000. And then, so let's look at two scenarios. Suppose we draw a sample of size 1,000 from the production line. So if that's the case, and then we can estimate the standard deviation, which is the square root of the variance and of P if we observe the defective rate is about 2%. So here we observe that P bar is 2%, so it's 0.02. What is the p-value? The answer is we don't really know. We don't really know the true p-value. So without any further information, we have to assume that the p-value is about the same. This is a reasonable assumption, but since we don't have anything better, we'll just assume the p-value is about 0.02. Now, the standard deviation is equal to the square root of the variance of p bar. And so the variance of p bar is equal to the formula says is p times 1 minus p divided by n, and then we do the square root, and if you plug in all the values, it's 0.02 times 1 minus 0.02, and divides by the sample size. Let's say it's 1,000, and then you take the square root. And eventually, this result will be approximately 0.0044. So that's the variance, which is not a very big number, which tells you that your estimation of P should be very accurate. Now, let's think about the second scenario. What if instead of doing a production line, which we assume the population is infinite, we do it from a lot and of 4,000. So we already manufactured 4,000 products. So this is the first part of the problem. And the second part, we're going to assume that the big N is 4,000. That's the whole population. That's it. No more is being produced. So in this case, we're going to calculate the square root of variance of P bar, and which is equal to the square root of P times 1 minus P divided by the small n times the factor n minus small n over the big N minus 1. So you can plug in everything. So the first factor is the same. So it's 0.02 times 1 minus 0.02 over 1,000 and times the big N minus small n. So it's 4,000 minus the small n, which is 1,000. Space time, it's 1,000 right here. And divides by 4,000 minus 1. So it's 4,000 minus 1. The whole thing is under the square root. I'll leave to you to do a calculation, and this is about 0.0038, which is even smaller than our result in the first part. So that tells us that from a finite population of 4,000, we do get a little bit better approximation than from this infinite population. All right, and we can also look at the next example, public opinion polling. So if we want to know the public opinion of general population, we can use sample of size about 800 or 1,600 or 3,200, etc. And now we would like to find the estimated standard deviation and of the observed proportion of national sampling if, let's say, the p-bar value is 0.8. So let's look at this example. And well, of course, if this is a national survey compared, this is still technically finite. However, we can more or less view this as infinite population just because the n is so big. So the variance of p-bar can be approximated by, or the square root of that, that's the standard deviation. We can simply use 1 minus p times p divided by n. And here, again, we don't know the p-value, but we can use the p-bar value to approximate it as 0.8 and times 1 minus 0.8, and then divides by the sample size. So here is the n. And then depends on the sample size, and we can have different standard deviations. For example, let's do our SQRT of, let's say, 1 minus 0.8 times 0.8. And let's do a sample size 800. So if we do that, we're going to get a standard deviation about 0.01, 1/4-ish. But if you double the sample size to 1600, and now the standard deviation drops to 0.01, it's only 0.01. If you double it again, and then the standard deviation is dropped to 0.007. And depends on your need. Of course, the larger the sample size is, the smaller the standard deviation is, or in other words, the more accurate your result would be. But of course, the price to pay is that it takes more time, the money, and the effort to sample that many people. All right, let's say a few words about these frequencies and probabilities and proportions. So here, let's take a look at the sample size 3 from the Williams family, and the p-bar is the observed proportion, and 1/2 the time the p-bar is equal to 1/3. We choose 1 voter and 2 non-voters, and the other half of time is equal to 2/3. These p-bar values are called probabilities or frequencies. We use these terms interchangeably. And well, one thing that we like to mention is that the total, the sum of all the different probabilities for the same problem would always be equal to 1. If you add up the frequency, or you can call it probability of all the possible outcomes, you should always get 1. And let's take a look at this example. Suppose you have the big n equals 10 and the small p equals 4, which means you have samples, you have a population of 10 items, and 4 of them has some special property. Let's say there are 10 people, 4 of them are voters. And then we can draw a sample of size 5 without replacement. And then depends on how many voters you find in your sample, you can have the different estimation of p. If none of them is a voter, which is possible, and then we have p-bar equals 1 and equals 0. If one of them is a voter, p-bar is 0.2, and then etc. The other extreme is when all of them are voters. That is actually will not even happen because there are only 4 voters. So the probability for p-bar equals 1 is actually 0. It's not going to happen. And the probability for p-bar equals 0.8 is possible. That's when you have 4 voters and 1 non-voter. That is possible. Not very likely, but it's possible. This is the probability here. And at the end of the day, if you add up all those numbers at the bottom, you will get precisely 1. You will get exactly 1. And that's the property of the probability. All right, this concludes Islam chapter 1. And thank you very much for watching. I will see you in the next chapter.